Hello, everyone. I'm Cecile Bonifacio from Fischione Instruments, and it's a pleasure to have you guys, everybody here on this webinar on the new argon ion milling technique using Fischione Instrument products. So before we begin, if we can ask everybody to please use the Q&A feature to submit your questions, and I will answer that at the end of the presentation. And if you have any other follow-up questions, please email sales@fishione.com. Okay, so here's an outline of the webinar for today. I'm going to differentiate broad versus concentrated argon ion milling. And for this webinar, I will be highlighting the NanoMill TEM specimen preparation system, what are the developments that we're having, and this new argon ion milling technique will be featured, and also some of the specimen preparation results for TEM analyses, and also for the SEM analyses, specifically transmission Kikuchi diffraction. All right, so let's get on this here on broad versus concentrated argon ion milling. So this is just showing you the scale, the length scale at which analyses can be carried out using different analytical tools. So what bridges the micron and the nanometer scale is the scanning electron microscopy technique, specifically transmission Kikuchi diffraction, which requires an electron-transparent specimen. So at the nanometer scale, some of the electron microscopy analysis techniques, this includes atom probe tomography, which uses a needle type specimen. Transmission electron microscopy technique, these are the conventional and high resolution techniques. Scanning transmission electron microscopy, this is the high angular dark field technique. And the precision electron diffraction. So at this length scale, atomic level imaging and analysis can be achieved. But of course, the requirement is we need to have electron-transparent specimens. So with that, Fischione Instruments have variety of argon ion mills, and we actually split two categories for that. We have the broad ion beam system and the concentrated ion beam system. So for this webinar, we're highlighting the concentrated ion beam system, specifically the NanoMill system. So before we go on, I want to differentiate the broad ion beam milling system versus the concentrated ion beam system. So the broad beam or BIB technique is the most familiar technique that everybody knows for argon ion milling. In this mode, the argon beam is stationary and we remove material from the specimen that is continuously rotating or moving back and forth. On the other method of concentrated argon ion beam milling, this is very similar to the FIB method, wherein you have a small beam that is scanned on the area of interest or where the milling box is placed. So the animation earlier actually shows how the beam moves or scans. This is usually in a serpentine pattern. So the main difference between the two techniques is actually the beam size. So for the broad ion beam milling technique, this is an optical image on the argon milling tool that actually shows you that the beam size is about 3 millimeters in size. On the other hand, looking at the concentrated argon ion beam system, so this is an ion beam image at 300 eV. Looking at the scale of the specimens are about 10 microns wide typically, and that's their area of interest where the milling box is placed, and within this region is where the 1 micron beam, usually 1 micron beam, scans. So those are very significant difference between the two. To further compare the two methods, so the broad ion beam is traditionally used for dimpled or wedge polished sample. And this technique usually yields large transparent areas. However, this is not site-specific. So I want to remind everybody that the beam size is typically about 2 to 3 millimeters in size. Because of this large beam, this can cause some redeposition of the grid material or the sample holder onto the specimen. And this is unavoidable just because of the large beam. Now, in contrast, the right column here on the concentrated argon milling system, this is ideal for fib prepared specimen, but also we can also process conventionally prepared samples. So in this system, we use a 1 micron beam, which is ideal for targeting fib samples. And an important feature of the system is that the argon beam scans over the user's selected area of interest. So because of these, we avoid the chance of redeposition of the grid material or the sample holder into the specimen. So for this reason, we have identified the concentrated ion beam argon milling as the best technique for producing high quality TM specimens. So specifically, the features are we're using an inert gas, which is argon, and this prevents any kind of chemical reactions with the specimen. Using a concentrated spot or 1 micron beam size, this actually avoids any kind of redeposition on the grid material or the specimen holder that you have. And in this system, we're talking about ultra low energies. So we're talking about 2 kV and below for final thinning. And another feature is that by scanning the beam, we're able to improve the targeting capability only on the region of interest. And also, we want to make sure that we're able to do high to low angle operation to optimize the specimen surface uniformity. So all these features are actually implemented in the NanoMill system. So here is the NanoMill system on the left here. So this is ideal, I guess, I've said earlier for fib specimens, and specifically for high resolution and analytical TM methods or STEM. So the key characteristics, again, we use argon. The beam size is 1 micron, and we have a wide range of milling angles from -10 degrees to +30 degrees. So that allows you to mill both sides of the specimen. And also we have the capability of specimen rotation. So the next slide here shows you the configuration inside the chamber of the NanoMill system. So here on the top, we have a secondary electron detector. This is actually how we visualize the specimen in the NanoMill system. And then down here, we have the stage where you can tilt in the positive and the negative direction. And the nice feature is that we have stage rotation capability. And this is nice for removal of curtaining on the specimen. On the right here is the ion source. So this ion source is stationary. And then across from the ion source is the Faraday cup. So this is used for accurate measurements for beam currents. So before we start discussing the new methodology of ion milling, I just want to discuss a little bit about how we do the traditional way or conventional milling geometry in the NanoMill system. So what you're seeing here in the slide is the grid, right? So the grid is oriented where the A, B, and C posts of the OmniProbe half grid is directed towards the ion source in this case. So this is how the grid is mounted. So because of this configuration, you can imagine that the thinning of the fib lamella will be from the fib capping layer, it can be PT, carbon, all the way down to the substrate, typical substrate of the sample. And the milling angles is usually done at ±10 degrees. So to further visualize this, so this is the specimen view. So what you're seeing here is the ion source, and the pink here or magenta is the when you turn on the beam. So and the specimen is tilted at 10 degrees. What happens actually if you look at the projected view from the ion source perspective is that typically you only see the edge of the specimen at 10 degrees. So and then also in terms of the milling boxes, we have started using square boxes, so 10 by 10 micron in size and as large as 30 by 30 microns. So this is the conventional or traditional way of nanomilling. So in this new technique, we now call it high tilt bottom-up milling geometry, and I explain where these links come from later on, you can see that now the TM grid is oriented 180 degrees, right? So in this case, the posts are actually facing away from the ion source. Because of this configuration, now the thinning is going to be from the back side or the bottom side of the sample on all the way to the fib capping layer. So what's the result if you compare both? So for example, at 15 degrees, the significant difference between the two is now that in the projected view, your region of interest, which is green here, is more visible. So in this case, your targeting is actually enhanced because the specimen surface is more visible. So now you can easily place your milling box when you're milling. So this is an example now how you target the specimen. Now this is an ion beam image at 500 eV at 15 degrees. Specimen is tilted at 15 degrees. So now you could see nicely that surface of the specimen. So you can easily place your raster box either in the middle, top, bottom, or even the whole specimen. And I will give examples as to when you want to use that. So in this case, there's some problems with the specimen manipulation because now we're tilting at a high angle, so typically in the positive direction. In order to do this in the traditional NanoMill holder, we actually have to flip the grid to mill the opposite side of the sample. So because of these problematic specimen manipulation, this can actually cause the loss of the specimen. We made some developments on a new NanoMill holder and other hardware. So now I'm presenting you the new hardware. So we have made a sample cartridge. So this is what holds the grid. And what we have done is this cartridge can actually be mounted on the NanoMill holder. So here's the new NanoMill holder. So this NanoMill holder is actually pre-tilted at minus 10 degrees. So that allows you to have more tilting range in the negative direction. So because of specific applications, we actually made some fixtures, for example, for TKD analysis. So this cartridge can get onto this TKD holder where it can actually go in the SEM and you can do your TKD analysis. So my colleague Pavel gave a really nice webinar on how to prepare samples for TKD, and we'll discuss some of his results later on as well. And as far as TEM imaging, so we have made this sample cartridge be mounted on a tomography holder cartridge for TEM imaging. So you can imagine that you never have to remove the grid anymore in this whole workflow. So your sample in itself is quite safe, and it's going to be much easier, high throughput with this new hardware. So this actually extends the NanoMill system's capability. So now you can do your specimen preparation easier, faster, and more accurate. So with the new hardware, you don't have to flip the samples and the specimen grid anymore. So that reduces the likelihood of the specimen, loss. And because we're now milling at a high tilt, as a result of this, you have faster milling in this case, and then also the targeting is more accurate. Okay, so now I'm going to try to show you some of the results using this technique. I just want to give you an overview of and make you see how this whole throughput actually gets enhanced. So from fib preparation all the way to TM imaging, this is how you can do your workflow. So first, you mount your just the grid by itself on our specimen cartridge, and you can clamp this whole cartridge in a clamping stub. Put it in the fib with your bulk material or sample that you want to lift out. You can do all your fib prep in this configuration using the cartridge. Once you're done, you just remove the cartridge from the stub and then move it into the NanoMill holder. So with the NanoMill holder, you can go straight to the NanoMill. And once you're done, you basically just have to remove the sample specimen cartridge and mount it into the cartridge of the ultra narrow gap tomography holder that we have. And then you can go in the TM. So you can also do iterative milling in this case, because with nanomilling, if you don't know the whole recipe, you may have to go back and forth in the nanomill. But in this case, the sample can is well maintained. You can never lose your sample in this whole hardware that we have. And then from the TM, you can do all your analytical techniques, your imaging techniques. So I'm going to start giving an example here. So this is an example of a metal film on an oxide layer. So this is actually tantalum, polycrystalline tantalum. So the center down below is silicon oxide, and it has a silicon substrate. So that's after gallium fib preparation. So how I did it, because my region of interest is only the tantalum, when I targeted this sample in the nanomill, what I did was I only made a 10 by 2 milling box and place it on the top area of the sample. So the reasoning for this is because that's the area that I want to thin, right? So and then I tilted the specimen in plus minus 20-degree direction. So now here is the result. So the image on the right here is after argon milling here. So what you're seeing is you see the PT capping on the top. So that's completely removed, but you could see from left to right that is removed uniformly. And then here now is the region of interest, and the overall stem intensity has changed, meaning the lower intensity actually indicates that you're thinning the specimen here. So at high magnification, again, still in STEM mode, so now we identify the different layers. So we have the tantalum, silicon oxide, and silicon here at the bottom. I just want to note that the silicon oxide usually gets milled faster than the metal. So in this case, you can see that this silicon oxide layer is still intact. So it's quite nice that we don't have differential milling even at higher tilt range. And just a zoom in image, and this is a TM image here. I just want to show that you start to see the grains within this tantalum layer, and you can already see that as well in the STEM image. So that's one key resource that we're showing here, that from left to right of your specimen, you have a very well intact layers in this case. So with argon ion milling, we're able to remove gallium and amorphization damage. So this is an example. So this is atomic resolution STEM imaging of silicon. So this is after gallium fib. What we have noticed is that you can see the silicon dumbbells, but behind that there is this high intensity contrast that you can see. And because gallium is a heavier element, that's the contribution of gallium into your sample. Another thing is doing fast Fourier transform analysis on the images, and typically the amorphous damage that we see is typically a diffuse halo in the background of these FFTs, and that's what we actually show here on this silicon sample, that you see this amorphization damage that's still present on the sample. However, after argon ion milling, so this sample was processed at 700 EV followed by 500 EV using a 10 by 1 micron box at 15 plus minus 15 degrees. Now you see the background intensity is uniform, and also the FFT is only from the crystalline silicon contribution. And by elemental analysis, by EDS, we're showing that we actually remove all that gallium on the specimen. So even at 5 kV gallium fib preparation, if you look at your EDS spectra, you'll see this gallium peak. It's always there. And after argon ion milling, we remove all that gallium. So one of the key things that I mentioned earlier is the nice feature of the rotation. So this specimen is a solid state drive device with air gap features. So you could see that with this kind of sample, you really will get some curtaining because you have the air gap structure here, and then you have the metal gate here. So it's usually typical that you will have curtaining on the sample. So by nanomilling, we're able to remove that curtaining effect. So how do we do that? So aside from doing the tilting, now you want to rotate the stage. So basically rotate the specimen and mill, rotate in the opposite direction, and then mill. So this is similar to the rocking technique and broad ion beams. This is how you actually do this. So this line here is a comparison of the line profile. Line intensity profile across the specimen. So you could see all these non-uniformity on the specimen, which we actually reduce after argon milling. And FTEM maps also show that. So it's the same exact sample. So this actually gives you some indication of relative thickness across the sample. And what we're showing here is that after gallium fib, there's areas of green and orange here. So after nanomilling, we were able to reduce that curtaining effect and make that thickness in that specific layer like uniformly. So also using this same exact sample, so we're able to do some analysis by EOS. So at 100 kV, so 100 kV EOS analysis really requires very thin specimen. So in this case, because we're able to thin this specimen from left to right, where we have a 10 micron wide specimen, we're able to now analyze multiple gates in this air gap structure type of specimen. So what you're seeing here on the top is the stem image, and the bottom here is a composite image of elemental maps by EOS. So you can imagine that, acquiring such data set, actually it took 14 hours to acquire these, but there's no specimen damage on the sample and no contamination that occurred. So with this, the milling conditions is down here, again, plus minus 15 degrees on these specimen. Now, this few example again, this is high quality ultra thin specimen. So this is 7 nanometer FinFET device. So just to give you a background, so this sample was prepared as a top down. So when we say top down, we have the fib capping layer in the top, and then you have all the device features nearby, and then the silicon substrate. Typically, when you mill from top down, that fib capping layer can sometimes get onto the area of interest. And what we're showing here is that we don't have any PT anywhere on the specimen. And by high resolution STEM on the fin structure, you can see the silicon dumbbell spacing is resolved. So this is a very thin sample. And by FTEM, you could see that the specimen thickness is uniform. Specimen thickness here is 12 nanometers. So this is processed at 700 EV and 500 EV. Okay, so these are quite nice results. So I'm going to go next for SEM imaging and analysis. So now the workflow is very similar to the TEM workflow. Again, you never would have to remove the grid when you're nanomilling or, nanomilling and going back and forth in the SEM. The only thing you'll manipulate is this specimen cartridge. So the next, for these specific analyses, we're doing transmission Kikuchi diffraction. So the difference with argon milling for these samples is that we are using the full size of the lamella. So one example is this sample here. It's a 5x3 sample. So the raster box size is dependent on the size of your lamella. Okay, so this is the data set that my colleague Pavel acquired. He showed this in his really nice webinar a few years ago. And what you're showing here is the IPF map, where you can see the different grain structure and of of uh, of the nickel sample here. So what you could see is this is the whole IPF map that was acquired for the whole specimen. So you could see that the map is quite all the grains are resolved in this case. And if you go in some area here, he analyzed further, and what we found, even just in the dark field electron contrast image, is that he's already able to resolve some defects structure. Some dislocation is already observed. And by doing kernel average misorientation analysis, he confirmed that these are the dislocations inside these grains. Again, this is very deformed specimen, so that's to be expected. Now, one thing you want to note for doing TKD, TKD specimens are usually prepared using the fib by gallium or plasma fib. But one thing to note is that, your sample will have gallium, right? Gallium implantation. So in this case, we want to show here is that by comparing the gallium prepared sample versus a sample that's argon milled, we're able to remove all that gallium. This is the red spectra here after argon milling. All the gallium is removed. And in this case, removal of gallium is very critical. And the reason for this is that your TKD signal gets obscured, and that's actually how you analyze all the grain structures and whatnot. So it's very important that not only you have a thin enough sample, but also you remove all that damage from the fib prep. So that's very important for TKD. And this is another example here. This is nanostructured nickel, another IPF map here. The specimen was 6 by 3 microns, and the whole lamella was analyzed. The whole TKD map was acquired. So based on the analysis, the specimen was found to be 20 nanometers grain size, average grain size, so very small grains on the sample. And the final thickness after nanomilling is 40 nanometers, so and very uniform across the specimen. So I'm gonna conclude here the webinar, and I was able to show you that the new hardware that we have actually helps with the specimen preservation and also reduce milling times and also increase your targeting accuracy. Over the years, we have some customers asking, "Oh, can we do this?" And I think this is the new, we're able to extend the capability of the NanoMill. And in this case, by the high tilt bottom up argon ion milling, we're able to get optimal TKD specimens of 3 grains or less. We're able to show you that we can get large electron-transparent areas of at least 6 micron wide. So we have shown you again and again. And of course, we're showing you that we can get high quality specimens free from gallium implantation, amorphization damage, and redeposition of the fib capping layer and also the grid material. So I also just want to acknowledge Trinity College, Clive Downing, and Professor Louis Jones, who acquired that really nice STEM and EELS data. And so with that, I'm happy to answer any questions. So I'm going to go through the Q&A box here. So, okay, so one question that we have are, what are the stage limits of the NanoMill? And -10 to +15, or the stage have a larger tilt range? So the NanoMill, the stage right now is at -10 degrees, and in the positive direction, we can go as high as 30 degrees. With the new hardware, okay, so because it's pre-tilted at -10 degrees, We can go as high as 20 degrees in this case. So the tilt range now becomes minus 20 degrees to plus 20 degrees. There's another question here that's popping up. Let me see. Okay, some actually put it in the chat, so I have to go look at the chat as well here. So could you please explain why it is now that you need, okay, why we don't need to flip the specimen anymore? So we do not need to flip the specimen using the new hardware. The reasoning for this is because of this, the negative direction, you have more tilt range, because now you basically have the tilt range as far as minus 20 degrees. So if you have the hardware, then you won't need to flip the specimen. So that's the reasoning for that. And then another question, is it possible to upgrade an older NanoMill with the new hardware? Of course, definitely. All you have to do is just buy the new hardware. If you are you're a user of the NanoMill, you have the system, all you have to do is just buy the new hardware. That's all you have to do. And everything would be compatible in your NanoMill system. So basically this whole new holder with the cartridge. So that's a very good question here. So I have another question that just came in, and one question is about can this argon ion milling beneficial for PFib users as well? If so, how? So we've shown these again and again that nanomilling can remove gallium from gallium fib preparation, and yes, I can tell you that we can also remove xenon implantation. So we all know that xenon can also create some amorphization damage, is significantly less than gallium, but we can remove that. And also, the nice thing about having a nanomill system is that for final thinning, if you want electron transparency, you want to use an animal system, because typically the PFib system, because of the large beams that they have, it's very difficult to make electron transparent samples. In this case, you can do your preparation in the PFib and leave it relatively thick, and you can do the final thinning using the nanomill system. So that's one thing um, that you can do. Another thing is that the specimen thickness of the specimen is not if you have the PFIB specimen between 200 to 300 nanometers thick, that's fine, because of the higher tilt, you have faster milling rates in this case. So we have another question here, a follow-up question on the hardware. Does the new hardware enable you to do sample rotation? So if yes, how? So yes, you can still do the stage rotation. And the reasoning for these is because that's something that we make sure this is feasible. The reason for that is that we make sure that the size of these cartridge won't impede on any of the internal parts of the nanomill system, meaning it will not hit the ion source, or it will not hit the Faraday cup or other parts of the internal parts of the nanomill. So yes, you can do stage rotation in this case. So yeah, you have a lot of things you can do with the new hardware. Does the new hardware work well for top-down milling too? Yes, definitely. You can still use the hardware for all the difference is if you use this for top-down milling, it's just the orientation of your grid, right? So instead of having the post being away from the ion source, you just have to mount it the conventional way that you do it. So yes, definitely you can do the conventional way. you can still do from high tilt to low tilt. It's not an issue here. So let's see. I think there's some stragglers coming in the webinar, but so I'm getting all these. So let's see here. We have more questions. Is the 1 micron beam size specified at 500 EV? And I would expect that lower voltage results in larger spot. And do you have any examples showing the advantages of sub 500 EV milling or any concern about? So this is correct. So the five at lower energies, the beam size would be larger. Okay. However, because we're able to control the beam scanning, um, this is not an issue as far as redeposition, because even though the beam is larger than 1 micron, it's still in this. We're talking about still microns, where this cannot be millimeter in size like the broad beam. We don't have redeposition issues because the raster box is always only going to be placed on your specimen. So that's one thing you want to do as a user, is make sure that you only target your specimen and not part of the grid. So and we've shown these again and again. As I have a lot of examples at 500 EV, right? Most of the preparation that we've been doing, or I've been doing, is I always go from high energy. So like example, this is 500 EV, and a lot of the TM prep or even TKD prep is done at 500 EV. You can go all the way down to 300 EV, and it's not an issue. So no, we don't see any redeposition. I've done EELS analyses. Because of the spatial resolution of EELS technique, looking at the sample to see any kind of redeposition from the grid material, and we don't see any kind of redeposition. Do we have more questions here? Okay. So let's see. There is one question about TKD. So one question that was asked is about how does the new milling approach improve the quality and reliability of TKD and TM analysis compared to traditional techniques? Do you observe similar issues with PFib, gallium fib, such as amorphization and ion implantation? So to answer the question, remember that again, this is kind of related. We're using low energies, and we have analyzed the amorphization damage. So basically what we have done is expose the surface of silicon with our argon beam at 900 EV and also 500 EV. That exposed surface was actually cross-sectioned, so we can actually see the damage, and we don't have any kind of amorphization damage, and we have that for sure. We have done analysis on that, and also implantation damage. So we have done APT samples, and we have tried to, that's argon milled, and we don't see argon implantation on that sample. And so we can say that no, we don't get implantation and amorphization at these energies that we're using for our samples. Let's see. I'm going back and forth with Q&A and also the chat, so bear with me here, but these are really good questions. So let's see. So one question is, how does combining backside thinning with the new holder setup affect preparation time and throughput in a typical workflow? So the answer here is that for sure, the overall workflow is the throughput is enhanced. The reasoning for this is that, like I said, first, you're milling at high angles, so that means the milling times are higher. And also about the specimen manipulation. There is really no manipulation. You're actually moving the cartridge in itself. So in this case, there's no specimen loss during each step. And that's very important as all the users of you're doing sample prep. You don't want to lose that sample because you spend like how many hours on the fib, right? So that's something that you want to do. So there is a question. For the new hardware, the sample has to be placed on the pole. How about if you... Okay, so the question here is about the configuration of the sample. So typically, for nanomilling, we have a flag configuration, meaning if you have the A, B, and C post, usually we tell customers to put it in the B post. So I know that there are specimens that are very sensitive to strain that you really need to mount it in the A and C post. This is actually feasible. It's actually better with the new hardware will still accommodate for milling and the A and B post. But the nice thing about it is because now you're milling at higher tilts, you can easily target the samples in the A and C post. The only thing that we always ask customers is if you're doing this kind of preparation, you want to make sure that you mill part of that, the V underneath. Make sure that you remove part of that, so that you can still see the sample also, and also to have the some vacuum where the beam is hitting for preventing any kind of redeposition. So yes, definitely not an issue for the V-shaped site, a post A and C, not an issue. Actually, it's gonna be easier for people who have that kind of sample. So do we have any more questions? I don't think so. I don't think we have any more questions, but please reach out to sales@fischione.com for any kind of questions. So with that, thank you so much for being here in our webinar, and hope to see you guys in the next webinar. Thank you.